For this problem, it says the continuous function f is defined on the closed interval from -4 to 3. The graph of f consists of 2 quarter circles and 1 line segment as shown in the figure over here. So this is the graph of f. It says let g of x equal 2x plus the integral from 0 to x f of t dt. Part A says first to find g of -3. Then we need to find g prime of x and evaluate g prime of -3. To find g of -3, we plug in -3 for x right here and then up here. So I have that written out. If you'll notice, these are out of order, so we're going to flip them and bring out a negative. Now right here it says the integral from -3 to 0 of f of t dt. And on the graph, if we go from -3 to 0, that's going to be this quarter circle with radius 3. So here I have written 1/4 the area of the circle with radius 3, so pi r squared, where r is 3. And our final answer is -6 minus 9/4 pi. Next, we want to find g prime, so we're going to take the derivative of this expression here. The derivative of 2x is 2. And to take the derivative of this integral, we're going to apply the fundamental theorem of calculus. So the derivative of the integral, the operations cancel out, and we take this x and we plug it into the function. So g prime of x is going to be 2 plus f of x. So now we have 2 plus f of -3, and from the graph, f of -3 is 0. So our final answer is 2. Part B says determine the x-coordinate of the point at which g has an absolute maximum on the interval from -4 to 3. Justify your answer. So for the maximum, we're going to take the derivative, which we found in part A, and it's 2 plus f of x, and we're going to set it equal to 0. So we get f of x equals -2. Referring to the graph, we want to note where does this graph hit a height of -2. Here I have the line f of x equals -2, and it looks like the corresponding x value will be 2.5. So our critical value is going to be when x equals 2.5 or 5/2. I set up a number line for g prime and put 5/2 as our critical value. To the left of 5/2, we already know that g prime of -3 is 2, which is positive. So right here I showed the work of plugging in 3, so g prime of 3 would be 2 plus f of 3. According to the graph, f of 3 is -3. So you get -1, which is negative, and then I wrote it out. Since g prime changes from positive to negative at x equals 5/2, g has a relative maximum at 5/2. So now we've determined that 5/2 is a candidate for the absolute maximum of g. We're going to check the candidate and we're going to check the two endpoints. And when we check these values, we're going to plug them into g to figure out which one produces the largest value. Our first endpoint is -4, so we're going to plug in -4 for x. I'm going to flip these to put them in the right order and bring out a negative. So now we have the integral from -4 to 0 of f of t dt. So that's going to be the area under the curve of f from -4 to 0. So here we have the graph of f from -4 to 0. You have this quarter circle, which is below the x-axis, so we're going to take its area and make it negative. Then we have this quarter circle, which is above, so that'll be a positive area, and we're going to combine them. The first quarter circle, which was below the x-axis, we have a negative in front. The radius was 1, so I put pi and then r squared, or 1 squared. And then the second quarter circle had a radius of 3, so we have 1/4 pi 3 squared, and it was positive because that quarter circle was above the x-axis. I took the negative and distributed, so you get positive 1/4 pi, and then you get negative 9/4 pi, which would make negative 8/4 pi, and that becomes -8 minus 2 pi. Next, we're going to check the critical value 5/2. So we're plugging 5/2 in for x. This represents the area under the curve of f from 0 to 5/2, or 2.5. So if we look at the graph of f, going from 0 all the way to 2.5, you have this triangle, which is above the x-axis. The base of this triangle is 1.5. The height of this triangle is 3. So we'll use those values to find the area of that triangle. Then we have this triangle right here. It's below the x-axis, so we'll use a negative. Its base is 1. And its height is 2. So here we have the first triangle above the x-axis, so it's a positive. It's 1/2, the base was 1.5, the height is 3. The next triangle was below the x-axis, so I made it negative, and it's 1/2, its base was 1, its height was 2. So we get 5 plus 9/4, and then minus 1. The 5 and the 1 make 4, and simplifying you get 6 and 1/4. And last, we're going to plug in the other endpoint, which is 3, and this represents the area under the curve of f from 0 to 3. And if you look at this graph from 0 all the way to 3, you have this triangle above the x-axis and the same triangle below the x-axis, so they'll cancel each other out because this area is positive, this one's negative, so you'll just get 0. So g of 3 equals 6. So when x is -4, g of -4 was equal to a negative value right here. When x was 5/2, g of 5/2 ended up being 6 and 1/4, And when x is 3, g of 3 ended up equaling 6. So our largest value would be the 6 1/4. And I just want to double check the original problem. It says determine the x-coordinate of the point at which g has an absolute maximum. Since the problem wants the x value and not the maximum value, I wrote it out. Therefore, g has an absolute maximum at x equals 5/2. Part C says, find all values of x on the interval -4 to 3 for which the graph of g has a point of inflection. Give a reason for your answer. So when you see point of inflection, that means we want the second derivative. So we know g prime of x equals 2 plus f of x. Therefore, g double prime of x is going to be f prime of x. We're going to look at the slopes of the tangent line of this graph of f. Here on the left, you have positive slopes, and then from 0 on, you have a negative slope. So g double prime, which equals f prime, changes sign from positive to negative at x equals 0. So I wrote that out. G double prime of x equals f prime of x changes sign at x equals 0. Therefore, g has a point of inflection at x equals 0. Part D says find the average rate of change of f on the interval from -4 to 3 inclusive. There is no point c in between -4 and 3, for which f prime of c is equal to that average rate of change. Explain why this statement does not contradict the mean value theorem. The average rate of change of f on the closed interval from -4 to 3 is going to be given by the formula f of 3 minus f of -4 all over 3 minus -4. From the graph, f of 3 is -3 and f of -4 is -1. So our average rate of change of f on the closed interval from -4 to 3 is going to be -2/7. The second part of the problem says there is no point c on that open interval for which f prime of c is equal to that average rate of change that we just found. And we want to explain why this doesn't contradict the mean value theorem. So the key to this is that the mean value theorem's hypotheses say that in order for the mean value theorem to hold true, the function must be continuous on the closed interval and differentiable on the open interval. If we look at the function f from -4 to 3, we can see that this function is continuous on the closed interval from -4 all the way to 3. However, right here at -3, you have a vertical tangent line, and right here at 0, you can kind of think of this like a corner. So the function f is not differentiable on the open interval from -4 to 3. So therefore, the hypotheses of the mean value theorem do not hold true. So I just wrote it out. This statement does not contradict the mean value theorem because f is not differentiable at x equals -3 and 0. Thanks for watching, and please hit the like button and subscribe to Math with Yosh. Thanks, guys!